Okay, so today what we're going to do is we're going to learn how to do the volume of a solid by method of cross sections. Okay, so this usually shows up on the AP free response, and it's usually not that bad. You just got to memorize some formulas. So I don't know if you can really see the detail in this project, and I don't want to mess my camera up too bad. But what we're doing is we're taking little shapes. So like in this case, it's rectangles, and we're building one big shape. So like this would make some sort of pyramid shape. And this was a project we used to do. So visually, that's what it's going to look like once we actually find the volume. So we're trying to find the volume by some sort of cross section. So there's a few formulas you need to make sure you remember. The area of a square is going to be side squared. The area of a rectangle is length times width or base times height. The base times height formula is going to be a little bit better for this section. Now, area of a equilateral triangle is going to be square root of 3 over 4 times side squared. It's very useful for you to remember that one. And then area of a triangle is going to be 1/2 the base times the height. And the last useful one that we're going to look at is semicircles. Okay, so a semicircle is pi over 2 r squared. Okay, so these are all areas of semicircles. Okay, so let's look at our first example. So previously we said that the volume of a solid is going to be the integral of the area. So we're going to set up the integrals. Needed to find the volume. Of a solid whose base is the area bounded by, let's do y is equal to x squared, and y is equal to negative 2x plus 3, and whose cross sections are perpendicular to the x-axis. Okay. So as we go through and do this, we're going to use the same steps we did before. We're going to graph two functions. And y is equal to x squared looks like this. And the line y is equal to negative 2x plus 3 looks something like this. Okay, so our ladder, if we're going about the x-axis, would look like this, just like we did before. Now what we're going to be doing is we're going to take various shapes and we're going to build a solid using this as the base. So first step, intersection points. So our intersection points, we set the functions equal to each other, just like we did in the previous two lessons. So we get x squared plus 2x minus 3 is equal to 0. So we're going to factor. So we get x plus 3 and x minus 1. So our limits come out to be x is equal to negative 3 and x is equal to 1. Now, say I want to set up an integral to find the volume for rectangles. With height of 4. So that'll be our first little example. So the area of a rectangle is base times height. So we have the height is 4. Your base is going to be the area bounded by this region right here. So your volume is going to be the integral from negative 3 to 1. Your base is going to be your top curve minus bottom curve. So it's going to be negative 2x plus 3 minus x squared, top curve minus bottom curve. And then we're just going to multiply it by 4. And that's going to be dx. Okay. Now, we're going to use the same region. Let's see if we can get that in the video too. Same region. Part B. Let's find the volume if they're semicircles. Now, what I suggest you do is just memorize the formula for this. It's pi over 8 times the integral of your r squared. And your r would just be your top curve minus bottom curve. Okay, negative 3 to 1. And top curve minus bottom curve is negative 2x plus 3 minus x squared. We're going to square it like that. So that's our setup for that. Now, where does it come from? Well, we already know that the diameter is twice the radius, correct? And so in order to get our radius, this region right here is going to be the diameter of the semicircle. So we would have something that looked like this, pi over 2 times r over 2 squared, d over 2 squared. Okay, so in this case, your diameter is going to be your top curve minus bottom curve. So what I would just remember is that it's pi over 8, and you get this formula from squaring it out. And you would get like this, pi over 8 d squared, okay? Or if you want to alter your formula to make it look like this d, top curve minus bottom curve, that's fine with me too. I would just remember pi over 8 times top curve minus bottom curve squared. Okay, let's look at another example. This is going to be a relatively short video because they're just setup questions. So number 2, example number 2. Okay, so set up the integrals. To find the volume of the solid whose base area is bounded by x squared plus y squared is equal to 9, and the cross sections are equilateral triangles perpendicular to the x-axis. Now, if we don't know what x squared plus y squared is equal to 9 looks like, that's the equation of a circle with a radius of 3. Okay, so that's your region right there. So if I were to do this would be a semicircle, correct? And so my limits would be from -3 to 3. Now, we know that a circle is going to be symmetrical, and so the area on top is equal to the area on bottom, so I would just double it. Okay? So your formula for volume is going to go -3 to 3, square root of 3 over 4. And your side is going to be top curve minus bottom curve. Okay? So your top curve is going to be this, and your bottom curve is going to be the negative branch. So what we would have to do, like we did up here, is since it's not solved for y equals, we got to solve for y equals. So y should come out to be plus or minus the square root of 9 minus x squared. Okay, because our cross sections are perpendicular to the x-axis. Okay, so we're going to solve for y equals. Now we're going to do a top curve minus bottom curve here. So your top curve is going to be the positive branch, and your bottom curve is going to be the negative branch. So this minus a negative of that means we're going to double it. Okay, so we can leave it either like this, or we can just combine our like terms. Okay, and there's really not any more need to simplify anything. Either one works for me as far as setting it up. I think you'd get full credit on your AP exam for either way. Okay, let's do one last example, and then I will post a video on the worksheet, some other examples from that, just so we can get a little bit better at this. So last example, example number 3. The base of the solid